More efficient. One just for others, one for others. What was the same sheet? If you have money,
You can link it.
but you don't need it in the first part.
Okay, so good evening, everyone. We'll start today's lecture. So this is, I guess, the 10th lecture, or in zero sequence, it's 9th lecture. Few announcements to begin with. Use the discussion board and try to give feedback for the lectures. I think in hindsight, we went a bit fast on the graphical models chunk of the course. We'll try to calibrate it next time. So, as well as in the exam review session next lecture. Assignment 2 is due in 1 week, excluding the break, and you have an exam in 2 weeks. So the week before the exam is in class. We have not yet finalized the duration of the exam, but 1 week before the exam, we're going to have a review of the concepts in terms of we'll work through some examples from both the topics that we have covered so far. So today we're going to address the problem of online learning, which is interesting. I don't know how many of you have been exposed to online learning before, but we'll try to define what the problem is and what some interesting solutions are. Okay. So again, just a reminder, there's a student research forum that I came across. So if you're interested, you can submit your project proposals here, or actually display your project proposals or whatever project work in progress as posters here. It's very useful because you will get free feedback, which can help you course correct your project and define the scope of your. I don't know. Hello. How do you change this? Oh, okay. Okay, so I mean it's useful for your presentation skills as well as to course correct your project if you're being too ambitious, or you can compare yourself to some of your peers. Although it's not necessary, it's highly encouraged to participate in this forum. Okay, so today we're going to look at we're going to go the inverse order, the way we dealt with graphical models. So today we're going to start with a very compelling application, which is the state-of-the-art application, and then look at a few. We'll touch some of the topics. One of the topics you might be familiar with, which is called A/B testing, and then a couple of new topics related to the same theme, which are called Multiarmed bandits and Contextual bandits, will be discussed. Okay, so let's kind of motivate ourselves regarding online machine learning through an example. So, how many of you have actually looked at some system or technique for online machine learning?
Like AWS?
It's okay. Huh?
Like AWS machine learning?
No, online means incremental, or you don't do it in a one-shot process where you have training data and then you create a model and then just use it. You may have incoming data in multiple rounds or multiple time instances. Then you have to update your model and then reuse it again and again. So that's what I mean by online. Any other thoughts? I mean, so most of the machine learning or data mining that you've been doing is offline. So you have already somebody has logged the data, and then you're computing classifiers or predictors, or even doing exploratory analysis, clustering, and so on, right? So here's one rough definition of what exactly we mean by online machine learning. So it basically involves 3 core steps. The first one is if you are a system which is going to be making predictions or taking some course of actions, automated course of actions, then the system, or you, let's say we are the system, we're going to observe the state of the world, as in we're given some input. For example, it can be a feature vector, right? We choose an action. It can be a prediction. It can be more general than that. And then we may get feedback on how the action was. We made a prediction that, okay, this user arrived, let me recommend that user a movie X, right? The user sees the movie and may not click on it or may click on it, and then you actually get immediate feedback that, okay, you took this prediction and it was probably correct or incorrect, or useful or not useful. And then based on the feedback, you do something. You do some course correction in terms of how you can make next recommendations and so on. And this process is repeated over and over again. Is the basic setup clear? Is the rough setup clear? It's like even if you had pre-trained your classifier, let's say a CNN classifier, you would be fed in a test image. You would predict its label or something. Maybe somebody will tell you whether the label was correct or not. Okay, then you can go back and change your CNN's weight parameter such that it kind of corrects for this error. Let's say if you made an error, and then again you were given a test image. You again make a prediction. Somebody tells you that the prediction is correct or not, and so on. Right? That could be one example here, but as we will see, it's actually fairly decoupled with the exact the types of supervised learning problems that we are looking at. Okay, so the goal is going to be to optimize feedback. So this feedback is going to be some signal which tells you that you're making right predictions or you're suggesting the right actions. Recommending the right things or making the right predictions. So you want to optimize feedback, as in you want to maximize, and feedback is the reward signal. You want to maximize the reward by choosing appropriate actions. Okay, and today's lecture, we're going to assume that the agent, which is, when I say agent, it's the computer system, you who's making the recommendations. Our actions do not influence the future context. So I make a wrong prediction on this test image. It's not going to tell me. It's not going to influence the future test image. So that's one assumption we'll make in this lecture, and we'll kind of relax it in the next lectures. So let's go through one very I guess running example or deployed example. So this is the problem of news recommendation. So this is the loop. Okay, this is the loop which we just saw in the previous slide abstractly. So user arrives at, let's say, msn.com with some browsing history, user account, previous visits, and so on. So there is some information about the user. So that can be the feature vector. The company which runs that website can choose the stories or ads or some other things that it wants to show on that web page, and the user is going to respond to that content through clicks, by spending time on that website, reading stuff, and so on. And you can log it. You can get this reward signal or feedback that how much time did the person spend on your website or on that page. Did they click on the news stories that you highlighted on that page, and so on, right? And your goal in this specific problem is to choose the content to yield desired user behavior. It can be you want to ensure that the user spends a lot of time on your website, or you want the user to click on as many content items as possible, and so on. And the assumption is that these recommendations to one user do not affect other users. Okay, so in the next time some other user comes, the recommendations or bad recommendations that you made have no influence on the second user picking the right, giving good feedback. So the feedbacks are independent of each other. Okay, is this example clear of what is the three-step process that's happening here? Any questions about this? At least the procedure of this setting. Okay, and this setting, as you can imagine, is also generalizable to a lot of other things like recommendation of movies, apps, books, and so on. And it can also be used to personalize search results that you see on Google or Bing or other search engines. There's a notion of customer churn that is, I guess, where also you can use these actions that you take. Yeah.
I have a question on this, sir.
Yes.
Sorry. So we are just going to rely on the information that, okay, what I mean to say is, if you get a new information, new kind of information.
About what?
Right now you're walking into the loop with certain kind of information about browsing history or something.
Yeah, so the information is about the user. Yeah.
Suppose this user has moved from, say, India to US.
Yeah.
Just changed. Okay?
Yes.
Or,
Yes.
or some other piece of information comes into the context. At
Yeah.
a later stage.
Yeah.
Will you go back upwards and change your learning strategy?
So it's like it's an atomic unit where a user comes, whatever is his representation in terms of the features that he has. Based on that, I'm supposed to choose the right items here. So if the user has moved from India to US or something like that, it hopefully is captured in the feature vector, and hopefully I can appropriately suggest the right items. So we're gonna completely spend today's lecture on how to design such a system which shows the right items through a bunch of interactions with the user.
I'll just clarify my question.
Yeah.
When someone moves from India to US or wherever,
Yeah.
that is already contained in the information in your browsing history or somewhere.
Let's say, yeah.
But something else, something new has been added. It's not the static. One more variable in your data is added. Let's say.
Oh, you're thinking of, let's say, feature vector and one additional coordinate has been added or something.
So will you change from that based on that?
So in the context of today's discussion, we're going to have finite dimensional fixed representations for context. So it's not going to change. So we're going to first take a top-down or a systems approach or engineering approach and try to understand how can we build a training or a learning system which works with this three-step loop, right? So some thoughts before we get to the loop is we may have information available on the actions that we took. So we showed a bunch of news items, and we know that for those news items, the user spent some time on the website or the web page, or the user clicked on some of the items. We don't know what would have happened if we had shown something else. Okay, so we only have feedback for the actions that we took, and we may, naively, we may have to try every plausible, good action. We may prefer to show 5 news items related to sports, or we may prefer to show 5 news items related to politics. We don't know which is the right action to show to make the user give us a good feedback signal, right? And so for every context, in the sense for every user's profile, we don't know which is a good action. So we may have to actually show all the actions, and if we can't actually show all the actions, maybe we have to randomize. So we'll get to the last bullet point later. But the idea is that, so this is us, as in this is not the user, this is the agent. Okay, so this is the system, the agent, the automated system, or the machine learning system. It's gonna, so okay, not just this is system, but this part is a system which is gonna choose, let's say, an image in this case, in this toy flow. So this is going to be the action of this system. Okay, it will basically follow a recommendation policy. Let's say you actually have a rule. Okay, if the user is under 30, then show a sports car. If it's greater than 30, and the person isn't from university, show a satellite. Okay, just maybe that's going to be your recommendation policy. Let's say, then you're just going to follow this rule and just show something, right? So what we're going to discuss today is going to sit on top of this part, which is going to be this recommendation policy. Okay, and it may have some randomness. That's why I'm showing a die. And this wrapper here is going to learn better policies. So I'm using the word policy. Policy is just trying to say, okay, if the user is of a certain type, then show these items, news items in this case, let's say. And if the user of a certain type, some other type, show these items, right? It's like a function which maps from user profile to what to show, right? In the news recommendation setting, right? the reason why I introduced this die is because later on we'll see that for us to for a decision service to learn better and better rules, it will need to track this probability of chosen action. So that we'll see towards the later part of this lecture. But for now, it's clear, right? Let's say we start with some baseline policy, some rules, some heuristics that you encoded on your website. Okay. How do you kind of change from some baseline rule to some other better rule in terms of the feedback signal? So if you change the recommendation policy, hopefully the user is going to spend more time on the web page or click more items on the web page. That's the type of signal that you get. Okay. Before we jump into the actual news recommendation system, which is for msn.com, let's just quickly go over why this is not a conventional wisdom yet. This is probably relatively one of the first few times you're seeing this content. So why is this not very popular, right? That's because in most tech systems or most businesses, there are separate teams for each part of the process to maintain data, to maintain the front end, to maintain the back end, to log or analyze data, right? So there are many separate teams. And even if you kind of knew what parts and what things are to be logged, you may just log the choice. What did the user do for what I showed? And you're not logging probabilities. And we'll get to this point, as I said, later. Sometimes features themselves of the user are not logged, and they can change over time, right? And there's also this issue of exogenous aspects like business logic. So your automated machine learning system may be suggesting show information about sports, but it could be because of your advertisers you want to show something about technology, right? So there may be business logic which is overriding your recommendation, the output of your recommendation policy. And you may also use the probability with which you chose, let's say, some of these actions that you took. You may use that as a feature, and it's going to be it may introduce bias. Okay. In the sense, basically, what I'm trying to say is that there are errors that you can make because of which you may end up doing something bad. It's hard to get such a system right. Okay, but let's focus on this case study in which they actually did get the system right. So we're going to look at an online machine learning system for this particular web property, msn.com, and they have 4 stages in their system. Okay, I think it's kind of clear. There's a deploy stage. We're going to discuss the explore stage. There's a logging of the data, and there's the learning part. And we're going to focus on learning and how it relates to exploration today. Okay, so this is a little bit more in detail of what the 4 parts look like. Okay. In their case, they put the 4 parts in the 4 corners, right? 4 directions. So it has. Okay, let's actually discuss. It has an explore part. Okay, so explore part is just executing a model. A model is going to be the recommendation policy, right? If the user profile is something, then show these items, right? That's going to be the model. It can be a decision tree or it can be something else. I don't want to fix a particular model, but explore is going to just execute a model. They call it a join server, but it's just a logging part where you log what was the user profile, what was the items that you showed, and what is the reward or whatever the feedback signal that you got. Okay, those are 3 things that you can log. As well as you should also log probabilities, but probability of why you chose a certain decision to show to that person. We'll need to log that, but we'll get there. And this online learning module is going to be the module that tweaks this model. So you had a baseline recommendation policy. It's going to change that policy to some other recommendation policy based on what feedback you got, right? So I'm just recapping the three-step loop that we have. And deploy is just loading up the module in some production environment, and and maybe here you care about computing decisions quickly and so on. So that's why it's been separated as a deploy step. And those are the 4 parts. Okay. And also, of course, you can use the data that you collect from your interactions with your users. You can dump it into another storage environment, and you can use that for offline learning. You can learn new features about your user. You can learn new correlations that the user exhibits with the information that you have about, let's say, your news items. So you can do feature engineering, you can also make predictions, you can make classifiers, stuff that we talked about in the first part of this course. Okay, and maybe that information can also be used by the online learner to improve the recommendation policy, right? So for the MSN particular case, the system, or in this case MSN had these types of features for this particular example. They had user demographics, user history, and then some information about some information about the articles that they want to show today. Okay, so they have 50 articles here, but some number of articles that they want to show on their msn.com page, right? So from this information, this part encodes from this information. Somehow the recommendation policy should output a bunch of items that will actually show on the page, right? That's going to be the decision, right? The action taken by the recommendation policy, and then the user sees those arranged in some manner, and then the clicks are logged as feedback. So that's the grounding of this particular flow. And the feed, this is how it's going to actually look like, but on the backside, this is what's happening in few seconds, a few milliseconds. And they were able to do this, actually, msn.com, the people. So for this, they have tens of millions of users, these many requests per second, and if they had a fixed policy, they had certain overhead in terms of providing, showing the personalized bunch of items. With this online ML loop, where they could get feedback, they could update the recommendation policy, and then based on the updated recommendation policy, show better news items, right? They were incurring about 5% more overhead, but they could set that loop appropriately. And they are updating the model every 5 minutes or something. So it's semi-batch, semi-online type of environment. And they observed a lot of gains. So this is from, I think, 2015, 2016. So just last year or the year before. So this is actually showing, so x-axis is showing dates, a sequence of dates. And the y-axis is showing relative improvement for a metric of their interest. In this case, I think it's click rates, click-through rates on that page. Okay, and by having this online ML system, they were able to relatively, have an improvement of about 25%, which actually is a huge number given the attractiveness of that page or that web property for advertisers and for their own brand and so on, right? So this is the change from having a static recommendation policy or a static machine learning system, which would just make recommendations to the users. Maybe after a week, you collect all the data, maybe add the data into your supervised classification or supervised learning setup, retrain your model, and then again update the model. So this is happening at a much higher frequency. So that's, I guess, on the spectrum of, on one end of the spectrum, you have the regular batch supervised learning, and the other end is what they've done. Right. So any questions about the application? So we're going to go into the specific details. We're going to ground on what the recommendation policy is, how they're going to change it, and so on in today's class. But any questions about the application? Yeah.
So are we saying that my action now will result in the next 5 minutes, the MSN will change the way it reacts with me?
No, so Amazon is going to show this page. You're going to do some action, and that action is logged immediately back to them. And in their case, in this production system, they are only changing the model or the recommendation policy every 5 minutes. So hundreds of users are seeing different, it's actually happening simultaneously. There are many users, but you can, let's say you fix one user is seeing one particular page, right? They are interacting with that page and giving us the, let's say, the click rates as the feedback. I'm going to use that feedback and update my model. You can think of it as happening even at the level of one interaction, right? One step through the loop that we saw. Is that?
So doesn't that mean that if I click on one thing and if I don't click on one thing,
Yeah.
the two paths after 5 minutes will be different?
So if you have two users who are seeing two screens and they gave feedback signal, based on the feedback signal, their next not just there, but in general, the recommendation policy is going to change for the subsequent users who arrive on the website. Right? I mean, it depends on their context of their profile, of course, but I'm saying that profile is captured in the recommendation policy. Right? Given the profile, what should I show? There's a feedback to that. So the model is getting updated. You may be showing something. Let's say somebody is interested in sports and you're showing technology, then they will not click on it, and so you will start showing start showing the appropriate sector for the next user who looks similar in terms of the user profile. Right? That's one way to reason about it.
So, will the recommendations for the current user not change after 5 minutes? Let's say the model gets updated and the recommender system gets updated. So you have new advertisements.
Yeah.
So after 5 minutes, the user should see some different recommendations. Will that be happening or not?
So actually, I glided over some topics. So they actually don't care about ads. So ads is handled by another team. So they are only focused on which news items to show here. So there are 50 news items from which you can think of. Let's say today you can have a bunch of editors pick a bunch of top 10 news items and then populate their page, right, out of the 50 news items, because you have real estate which is small and you want to capture the user. Now you're asking, okay, I interacted with this page, maybe I clicked on something that's going to influence, you're asking whether that will influence my subsequent view of this page. Yes, it should, because that will be captured, and hopefully if it has been used as a part of the updating of the model, then it will be reflected here. Yeah.
So,
Yeah.
one of the assumption that you said was learning from one user will be applicable only to that user and not to some other user. That was the
So it's not, the learning is not user specific, right? We have our recommendation policy that takes input as this context or user profile. So whether the user is reappearing or whether there's a different user, that's just input to my recommendation policy. I'm blind to which user it is. It could be the same person. It could be a different person with the same profile. Right? Any other question? Okay. So let's get to some basic ways to get to this type of an online system. So actually in that system they use a version of something called Contextual Bandit. Okay, in this particular application where they were trying to choose news items based on the user profile, right? So the user profile was a context.
Sorry, I'm not back to the previous slide.
Yeah.
25% increase is only specific to this news.
Just news. Yeah.
Just news.
Yeah.
Okay.
So we'll see that for other web properties, there are other ways to do this online system, right? So in fact, I won't capture that case, but A/B testing is heavily used for let's say Bing search, right? It's a different web property by the same company, and they do A/B testing to figure out how to. So here there's not going to be context. They're just trying to figure out what is the best way to represent results and so on, so as to maximize clicks or maximize search relevance and so on. So it's a different.
Holding a user for 5 minutes on
Yeah.
website
Yeah.
is a very difficult scenario with respect to clicks on,
Yes.
on some ad or
Yeah.
so, and
Yeah, so this is a content website, right? So msn.com is a content website. Yeah, so we'll first cover A/B testing, which is not actually, which actually ignores the online aspect of the problem, but is still relevant because they will use these feedbacks, but they'll use these feedbacks after a period of time. Okay, so imagine the same system, but now you are suddenly in the offline setting. So, but then we have generalized the actions that the automated system or we can take as being recommendation policies, right? These are not just predictions. So that's I guess a slight difference of why we are not just using supervised learning or something like that. Okay, we're going to look at A/B testing. So we'll ignore the online aspect of the problem, and which means that we'll ignore the instantaneous feedback that we're getting. So we'll collect a bunch of feedback. Okay. In particular, what we'll try to do is we'll try to decide on good recommendation policies or some good options for what I need to do in the next period. Okay, so let's start with a very simple example. So here are two web pages of a particular service. Okay, and they care about conversion rate. So these are not really recommendation policies. These are just very static things. They want to either show the web page A or web page B. Okay, and there is a slight difference between them. There is some enter coupon code box there. Okay, and they want to know which one should they be showing to the users, right? That's also a decision. So what is your guess? What do you think between these two? Which one would be useful if they want to maximize conversion rate? Huh? Enter coupon code. Okay, actually they lost a lot of revenue because of the right one. Because I mean, I think in this case they reasoned that users want to find coupons to reduce price. They think that they're not getting the right price because there's a possibility of coupons being there, and so they're more reluctant to finish the transaction here. So okay, so this you can learn by some way, right? So that's what we're going to see today. So what's the general scenario? So let's say there's a meeting to decide on how to improve a particular product or service, and there are multiple competing ideas, or multiple competing features that can be done, right? That can be integrated into your product. You want to make this decision after making some field observations. Okay, field observations means you actually deploy that feature or enhancement in the field, as in the real world. Whoever actually show it to customers, and then you're trying to figure out, and then you figure out which one to pick. Okay, that's what I mean by field observations, and this is basically one way to do this is to use A/B testing, and it's related to something called two-sample hypothesis testing. So, how many of you have seen hypothesis testing before? Okay, that's great. How many of you have never seen hypothesis testing before? Just one or more? If somebody has not seen, you should tell, because okay, so actually we are not going to cover hypothesis testing, but still but A/B testing is actually one of the simpler things to understand, so hopefully we can understand the concept here. So A/B testing, as the name implies, is about showing users or showing users of your system two solutions or two variations, and you figure out if solution A is different than solution B in terms of a particular objective that you decide a priori. Okay. As I said, let's say you can consider A to be a control and B to be a treatment. These are specific technical I guess names used. And what you do is randomly split the users that you have that are arriving online, let's say, while you show either the control or the treatment. So you have users. Let's say they are visiting your, let's say, web property. Then maybe randomly split them into two groups, and for the first group you show an existing system, and the second group you show an existing system, but maybe a slight change. That could be that feature X. And then after some time, you collect these outcomes and then decide which option is better, and that you do by doing some analysis. Typically, this is going to be hypothesis testing, and this is a good way to actually decide which option is better because of two things. Firstly, this random splitting of users is a good way to establish a cause-effect relationship. Okay. Have you heard of randomized controlled trials, RCTs? So in the clinical setting, when somebody wants to actually get approved as a drug on the market, then one of the stages that they have to go through is do randomized controlled trials where they're going to split, let's say patients for which the drug is hypothesized to be effective into two groups, and for one group of those patients, they're going to administer the drug, and the other set they're going to have a placebo whatever mechanism, and they're going to actually see and then at the end of that experiment, they're going to kind of attribute any changes to the patient's condition to the drug administered. Okay, and it critically relies on the fact that the two groups are exactly the same except for except for one change, which was the drug was administered to one of the groups. And the randomized control is because you want to split this group such that the two populations are exactly very similar to each other. I mean, ideally they should be the same, but you can't do both. So you can't have a person on both sides. So that's why there's a randomized splitting of the users such that hopefully both sides are very similar to each other in every other characteristic, except for the thing being administered, and that's in this case is they're seeing feature in one side and no feature on the other side. It's the same idea. And this, let's say you collected data offline, you will have a lot of issues, selection bias. You will have issues related to, because from offline data you mostly can do correlation analysis. So this is a good way to actually attribute that a particular feature was actually improving a particular objective. Okay, so it's just a rebranding of some of the things that you've already seen in hypothesis testing. So there's that. Okay, so in terms of the interestingness of this particular technique, there are full-time companies you might have heard of which actually do A/B testing, right? So there's Optimizely. So almost many websites that you visit actually load their particular JavaScript as well, if you actually see them. So there's Optimizely, Optimize, APT, and others who actually provide A/B testing. They're also extensively used, for example, at Microsoft for Bing.com, which is extensively documented at this website. So there they use A/B testing to again capture some other measures, right? So in the news recommendation case, we said click rates. In the Bing.com case, it could be something else, right? It could be the relevance of the search or other things. A/B testing is actually run at a very high scale at Google, Facebook, Amazon, and these other companies. I think for Microsoft's Bing.com, they run about, from what I heard, what I remember is about 300 tests per week. Okay, so whatever is their population of people who actually go to Bing.com and do some search, almost the entire cohort, entire population is broken down into many chunks. And since there are 300 tests being done per week, maybe there are simultaneously about 20 tests going on. So you break the groups into 20 subgroups and show different Bing results potentially, or Bing pages with their query results, and see what are the features which are affecting or improving their particular criteria, right? So that's just for Bing, and definitely being done for Facebook and Google. I think Facebook had an issue, has actually some negative press about some social experiment that they did where they were showing only positive feeds of their friends versus another cohort where they were showing negative feeds of the friends, and trying to understand what is the impact of the newsfeed on the happiness or something like that. I don't know if you've come across this particular article. I just remembered it on the fly. Okay. Yeah.
When they run tests at Bing.com,
Yeah.
Do they see simultaneously if one user can be like part of both the tests?
They'll have to do all that course correction. So in fact, we'll okay, since A/B testing is, we are not going to spend too much time on it. They have to do all those checks and balances to ensure that, in fact, for example, in this A/B test case, the control and the treatment are very similar to each other. There is no exogenous effect which is causing a difference other than what they are showing, right? So to control for that is very, very difficult, especially when you have a lot of covariates, right? So that's why they have maybe 10 papers here which describe how they went about doing it. Okay. It's also, as I said, it's very important in clinical trials. So randomized controlled trials are actually A/B tests, and they're also used in marketing. Okay. So I'm not going to spend too much time on A/B testing except for a few facts. So A/B testing is about collecting statistics across two groups, and this randomized assignment of the two solutions or two versions is a key requirement because it eliminates bias and confounding. Okay, and so let's say each group of users has a true mean effect. Okay, whatever effect that you're trying to capture is nu1 and nu2. Then basically A/B testing is trying to answer the question whether we can say that these are different in terms of, let's say you estimate these effects and try to suggest post hoc after you have collected all these feedbacks whether the estimates give us any confidence in saying that these two true means are different or not. Okay, and same thing if they are same or which one is larger and so on, right? And there are many types of hypothesis tests that you have seen before in other classes. So Fisher tests basically are all about rejecting the null hypothesis, okay, and rejecting or not rejecting the null hypothesis. Name and Pearson tests are about likelihood ratios, and so there's a lot of additional parameters that you need to control and take care of, right? Type 1 errors, type 2 errors, and so on. And Bayesian testing is all about computing the probability of a hypothesis given data, right? It's a posterior of the posterior probability of a model or of a hypothesis given data, and it's going to be similar to name and Pearson when the priors are the same. Okay, Bayes rule. And basically, we are not going to spend time on hypothesis testing, except saying that any of these frameworks can be used to favor one of these solutions, solution A versus solution B, and there are many variants that will come across if you just search for A/B testing on the internet. Each framework may has its pros and cons, and we'll not discuss them here. For example, for the Bayesian testing, you will have to define an appropriate prior, and that's going to be difficult. So your prior may completely sensitize your results, your outcomes that if you're just saying B is better than A, maybe you had a prior that B is actually better than A, although the data was against that, you concluded B is better than A. So, but still, Bayesian testing is, I would say, more preferred than the other things, the other two frameworks, because of distributional assumptions and so on. Okay, so A/B testing, what are the pros of A/B testing? It's very intuitive to set up. It's just splitting your users randomly, okay, and making them experience the version A or version B, and making some conclusion after some hypothesis testing. So field experiment decides the worth of a feature offering. So you're not going by gut instincts, so which is a data-driven way of deciding things. And it's very, very heavily used in industry compared to the techniques that we're going to see later, except for the last one, which is contextual bandits, which are actually used for the first case study that we saw, the news recommender system. And you don't even have to do it in one time. You can repeat this as you think that the users have changed and so on. So what's best today may not be the same tomorrow. So you can kind of redo this test. Okay. So what are the cons? It has many bells and whistles to make it work, and especially because most it could be that the product that you're actually selling, let's say Bing.com, the baseline version is already very optimal. So it's hard to come up with a version B, okay, where you can actually show where you can actually show an improvement, or that it is even matching the same effect as the baseline, right? And if the treatment effects are very small, then you really have to kind of spend a lot of time trying to isolate that signal from all the noise. Okay, so these guys at Bing have documented it extensively and made it public, so you can have a look at what are the different considerations that they had to take into account for doing A/B testing in production. Okay, and to just lead into the next couple of topics. So in A/B testing, we had to do this offline, right? We had to randomly split a bunch of users. We actually had to decide how many users that we're gonna use in that study. Let's say 10,000. We randomly had to split the users into two groups. Let's say 5,000, 5,000. And at the end of the at the end of collecting all that feedback, we were actually doing the hypothesis testing. But what if we can change who sees what treatment, or who sees what, in the sense of who sees A and who sees B dynamically. Okay, maybe you know that control A, Bing.com, is having an effect nu1, and some other variation is having an effect nu2, and you know that effect is very bad. So they are very different from each other. Okay, then why do you have to spend 5,000 of those users, make them experience the version B and have bad results, right? You should be able to ideally dynamically change, in the sense at after every interaction with the user, you should be able to kind of iteratively figure out which option is better. Okay, A or B. So that leads to the multi-armed bandit problem. And what if we also want to optimize over several options dynamically? So A/B testing is all about just two options. Somebody somehow through some process created a feature, embedded the feature into product, and you have, let's say, two versions, and you're just comparing which one is better. It's just two, right? Or maybe you can have more, but finite number. But what if you wanted to bring in an optimization into the loop, where there's an automatic, there's an algorithm which is already trying to zoom into or trying to pick the right option in a dynamic way. In a sense, optimization is all about search, right? You're trying to go from a candidate solution to a candidate solution where it's the best for whatever the criteria. So can you bring in optimization into this problem? So what the A/B testing that we've seen is an offline problem, and so we're going to try to move towards online versions now. So any questions here? Because we didn't go into hypothesis testing, so there's not much technical meat here, but any questions in terms of A/B testing? Any confusions? Yeah.
Can we repeat the contextual bandit?
We'll get to the contextual bandit in the later part of this lecture. So contextual bandit is very, so if you remember the news recommendation example, so context is the user profile. Here there's no context, right? A/B testing is about, I have two features, I want to know which feature is better. Let's say a control and a treatment, I want to know whether treatment is better than control. Okay, so I don't, okay, if I have features for the user, I just want to ensure that features of the users in one group is similar or very close, or has similar distribution to the features of the users in the other group, so that they are almost the same group. So that's the use of the features there, but otherwise features are not really used in this version that I presented, right? The features part will come when you think about the news vendor, sorry, not news vendor, the news recommendation problem. Any other question? Okay, so let's look at the multi-armed bandit problem. So how many of you have heard about the multi-armed bandit problem? Never heard of it? Okay, I'm assuming that most people have not heard of it, so we're gonna actually go over this problem slowly. So this doesn't require We'll start from scratch. So multi-armed bandit problem is also a sequential interaction problem. Okay, so it involves the following procedure in each interaction. Okay, so what is an interaction? So I am again an agent or somebody who wants to optimize something, right? I'm the company or I'm the agent, or so I want to pull arms. Okay, so pulling the arm is just saying taking an action. Okay, I want to pull arms. Okay, for example, in this case, which ads to show or which color to pick on my website or something like that. And when I pull an arm or make a choice, instantaneously I'll get a reward, which is a measure of success, which is going to be a user click or an item which is purchased, let's say. Okay, so that's it. So it's a interaction where I'm not, now there's no context. I will take a decision, maybe I'll show an ad A or change the color of the website from blue to red, maybe show color red, and then I'll get a measure of success, whether they stayed on my website or whether they left or something like that, right? There's only two things which are happening. Okay, so more abstractly, what the problem is as follows. I have k arms or actions. Okay, and for now I'm going to assume that these actions correspond to an unknown distribution nu k with values bounded in 0, 1. Which just means that think of nu k as a distribution which is bounded between 0, 1. It doesn't have to be a bounded distribution, but like a uniform distribution between 0, 1 is just a distribution, right? So you can have any distribution there. So you have k distributions associated with each action. Why am I bringing in distributions? Because at each time t, when I pull an arm or take an action it, with this action it is going to be the action at time step t, and it's going to be one of these k actions. If I take that action, I'll observe a reward x subscript t, which is going to be drawn from the distribution. Okay. And let's say I take another action at I subscript t plus 1, there's going to be another reward x subscript t plus 1, and if it happens to be the same distribution, if it happens to be the same arm, it's going to be independent. Okay, that's all I mean by IID sample from the distribution. And the objective is to maximize the expected sum of these rewards. So I'm calling this xt that I get, the feedback that I get, as the reward. Okay, and my objective is to maximize the expected sum of rewards. If I do this step t times, I'll get t reward numbers, right? X subscript t from 1 to, let's say, I run this for 100 steps, I'll get x1 to x100. Those all be samples from their appropriate distributions. They depend on the action that I take, and I want to maximize the expected values of those numbers. Okay. Is the definition clear? So what is this expectation over?
All the actions, yeah.
Yeah, I mean it's an expected sum. So expectation is a linear operator, so you can interchange the sum and the expectation. So it's just expectation is there because there's randomness, right? The reward is a random number, right? That's all. I just yeah, that's why there's an expectation. So is the problem clear? So the k arms, k options that you can take at each round. Okay, let me index a round with subscript t. And each round you took an action, you got a reward, and the reward is just drawn from a distribution which is dependent on that action, right?
Is there a probability associated with which action you can perform?
That's up to you to decide. So your policy, or I mean your strategy, can be I want to pick always the first action, and your another policy can be I can pick an action according to a distribution that I maintain. So you can bring in randomness like that, right? You can bring in a distribution over actions like that. But the way the interaction between the system or the agent and the other party or other party as in whenever I take an action, somebody has to give me a reward, right? So this is how the interaction happens. Yeah.
So the reward is always generally the user clicks the site or not, or
It can be binary, yeah.
But it will be always binary.
It can be. No, it can be just you showed a page. How long did the user stay on the page? That's potentially a real number, right? It may be content page, right?
How are you going to? We are going to click on that page, right? How will you?
No, if
tell
the
that
person
I-
closes the tab, you know that the connection was lost, and you can say that that was the reward signal for that content. The content was interesting or not. I mean, okay, this is all not just related to websites, so it can be any setting. So actually, multi-armed bandits were used in clinical trials actually, which again brings us back to the A/B testing, where in this case you can say I have D different drugs, and which drug, if I administer this drug today, then some bunch of people got well. Tomorrow I administer some other drug, some bunch of people got well. So now it's a discrete number, not zero. Let's say not 0 or 1, right? So mean of each arm is I'm going to represent as new subscript k, and the mean of the best arm is new star. Okay. So is the procedure clear? What's happening? So there is no context here, right? Every round, at every step, I'm just showing something and getting a reward, right? And what do I want to do? I want to maximize the expected sum of rewards, which just means the same as what we saw in the first slide. You know, these feedbacks are the rewards, and I want to show the right things, or pull the right arm, or basically take the right action, such that I kind of get the right reward. Sorry, not right, but the best reward, expected reward. Okay. So firstly, it is an online problem. We just deleted the context, so otherwise it is the same, right? We are taking an action and we're getting a feedback signal. And we need to come up with a strategy to figure out what actions to take in each round, right? For example, I can have a round robin strategy, by which I just mean that I have k actions to take. First interaction, I'll take the first action. Second interaction, I'll take the second action. Third interaction, I'll take the third action, so on. Kth interaction, I'll take the kth action. K plus 1th interaction, I'll take the first action, so on. Right? It's just round robin. Or I can also take a constant strategy. I have k actions to take, but I don't even want to try the other actions. I just keep the same action. Maybe show the same ad, or maybe keep the color of the website the same, or something like that, right? And to evaluate the performance of strategy of how you're picking these actions, right? We're going to define something called the cumulative regret. It's just going to be for a particular, set of interactions that you had. Regret is just going to be the difference between the expected reward you could have gotten if you had shown the right action, or sorry, if you had pulled the right arm, right? If you had made the right choice. Let's say you're running for n rounds, lowercase n number of rounds. Then this is the expected reward that you can get by showing the best action, right? Minus the reward that you actually got. So from 1 to n, every round you're getting a reward xt, a feedback signal. I'm just summing them over, right? And since these are rewards, this term will hopefully be higher than that term. Actually, that's not true here, but if you take an expectation over Rn, because Rn is a random number, okay? Why is that a random number? Because xt is random, right? You can think of xt as a random variable, right? If you take an expectation over Rn, this is anyway constant, there's nothing. You take expectations over xt, you'll get new subscript t's, the action that you took in that round, the mean value of that, which we defined in the previous slide, these new case, right? So the expectation is just this, okay? And so there is this best action that we don't know a priori. If we knew that action, we would just take that action every round and get the most reward, right? To maximize the expected sum of rewards, if I know the distributions, I can compute their means, I can sort the means, I can pick the mean with the highest, which is the highest, and just show that action. So, pull that arm or take that action, and that will actually maximize my expected sum of rewards, right? Do you agree? It's just that I don't know these distributions, and so I don't know the means, and so I have to figure it out if I want to maximize the expected sum of rewards. The same maximization of expected sum of rewards, we are just comparing it with what could you have done if you had known the distributions, and so that's why I'm just comparing two numbers. What did you do in terms of performance? In a particular run, this is just going to be the realization of the random variables of the n rounds, and if you take the expectation, it will tell you the expected reward that you got because of that choice that you made, right? And what you could have done if you knew the true best action. Okay, that's just the same notion as rewards, is just a regret notion. Okay, cumulative because it's just summing over n rounds. Okay, if you think of average regret, then you divide by n, let's say. So is the objective clear and what's happening in each round clear? The only thing missing is strategy. How do we pick actions to take in each round, right? Any confusion? Yeah.
Can you go back to the previous slide? How do you make that mean of each arm the expectation x, and what does it mean?
No, I'm just representing the mean of arm k to be nu k. Sorry, it's just spread over. So nu k is just expectation of that arm, right? So that arm is associated with a distribution nu k. Sorry, mu k. And this is just expectation of a random variable, scalar random variable.
So Vk is a random variable between 0 and 1.
No, it's a distribution, right?
Yeah.
That is not a random variable. X is a random variable which is drawn from the. So every time you pick that action, I just index, look up the index of which distribution I picked up, and from there I sample. So you can think of capital X to be like a random variable associated with a new subscript it, right? So, okay, let's think of two arms, right? So there's a distribution. It's just for simplicity that we said that there's a distribution between 0 and 1, let's say. Let's say these are the two distributions. And if you draw from here, you'll get some random variable x. Draw from here, get some other random variable x. So these are the quantities for two action instance. Okay, k is 2. Right. So if I have 10 rounds, right? Maybe not 10 rounds. Let's say 4 rounds. It could be a strategy, right? Could we just pick always the first action, and strategy, let's say A. Strategy B can be pick an action, pick some other action, pick an action, pick another action. So this is the round robin that I was discussing, and this was the constant I was discussing. But there could be other strategies, right? You could do something else. Ultimately, you're supposed to maximize the expected total reward collected over n rounds, 4 or whatever, 400, right? Whatever is the n here. And you're supposed to start trying out these arms, but you want to figure out which arm gives you the highest mean value and go with that arm. Okay, so we're gonna start with
Theoretically, the optimal strategy will be a constant strategy, right?
Yeah, if you knew the, if you knew the distributions, this is the strategy, right? There's going to be argmax of k. So one of those k is going to give you the highest expected reward. You just play that every round. Yeah. But you don't know that information. So the first algorithm that we're going to look at, which actually does something interesting, is this. It's called the epsilon greedy algorithm. So the idea is that we need to explore the arms because we don't know what are the distributions governing those rewards, right? But we also need to exploit what we have learned so far. In the sense, if we knew the distributions, then we know which one is the right distribution. If we know the distributions, we know the means. If we know the means, we know which arm to pick. So at some point of time, let's say we tried a bunch of arms. Okay, after 4 rounds, we tried a bunch of arms. We tried a bunch of arms. Right? We have observed some feedback signal up to some time. Then, based on that observed sequence of signals, you can estimate which one is the better arm. Right? That's what I mean by exploitation, and that's this view where you best idea or best arm found so far, you can use that, right? But you also need to explore in the sense, for example, when you're at the very beginning, you don't know if you're taking one sample from each arm, and let's say they are actually Bernoulli distributed. So instead of continuous distributions, they are just 0 or 1. Flip a coin. So you have let's say in this case 2 actions. If you flip the first coin, you got a heads. Flip the second coin, you got a tails. Doesn't mean that the first coin is gonna give you always a higher reward than the second coin, right? So that's why you need to explore, as in try out these arms so that you learn something, right? And so it's just the strategy is going to be as follows. Okay, it's just pictorially shown like this way. So what it basically is doing is epsilon is a parameter for this algorithm, and with 1 minus epsilon probability, so it's a randomized algorithm now. Okay, I'll flip an internal coin. Okay, which has a bias, let's say 1 minus epsilon. Epsilon is a parameter. I'm going to flip that coin. If it lands heads, I'm going to use the arm that I've seen, which is the best so far. Okay, empirical. I can compute the empirical means, right? I'll use the arm which is the best so far, and it flips to tails. I'm going to randomly pick an arm from the whole set of arms. I have k arms. I can pick one of them uniformly at random. Okay.
Shouldn't you pick from k minus 1 because you already know one best?
Yeah, I mean you can modify the exercise. It doesn't matter. Are you saying these don't add up to 1?
No, what I'm saying is with some probability you pick the best arm.
Yeah.
So with the other probability you divide.
No, with the other probability you can kind of ignore that you know the best arm and you can pick from at random. Yeah, there's some chance that you'll pick the best arm again, which is okay. I mean, you'll pick the best arm with 1 minus epsilon plus epsilon by k or something.
Yeah.
So, yeah, it's okay. I mean, it's just a minor variant. But is this algorithm clear? It's a randomized algorithm. It's basically the idea that it's basically a randomized algorithm which is randomizing between exploiting whatever I know so far versus trying out something new, right?
Why is that greedy?
It's greedy because whatever information I know so far, it's trying that out with probability 1 minus epsilon. So it's greedy as in it's whatever information it knows now is just acting greedily according to it.
So you're saying like 1 minus epsilon is higher than epsilon times k? That is why it's
No, epsilon is an arbitrary option. Typically, epsilon, let's say, is 0.1. So you try to exploit most of the time and explore some of the time. Yeah, it's just you can name the algorithm whatever you want, but this is what it does.
It's greedy because 1 minus epsilon is generally higher than epsilon by k.
Yeah, you can reason it that way. Yeah. Is the algorithm clear? It's a very simple algorithm. So for this algorithm, actually, people can show that the expected cumulative regret, that term that we had seen, right, expectation of Rn, right? Now that expectation actually has to, the expectation of Rn, that expectation has taken into account algorithms randomness, my con flipping that I'm doing, and also takes into account the randomness, that mu1 to mu k. I mean, these distributions also come into play when you take that expectation, is what I'm saying. According to whatever you chose, that particular mu will kind of be used, right, for that term. So anyway, in terms of expected cumulative regret, this algorithm, the epsilon greedy algorithm, actually has a performance upper bound. In the sense, somebody has actually sat down and proved that this expected total reward that you, expected cumulative regret is actually upper bounded by c times k. So if you have two arms, then it's some function of 2, linear function of 2. Okay, and as a function of the number of rounds, right? It's logarithmic. Okay. Why am I so okay? X-axis is actually I have not plotted the x-axis and y-axis. Y-axis is just cumulative reward, expected cumulative reward. Okay. And x-axis is just the rounds. Okay. Sorry, x-axis rounds here, and here it's number of arms. Okay. So basically, okay, there are two plots here. Left plot is trying to plot number of arms versus expected cumulative reward, and the second plot is, or the right plot is showing expected reward versus the number of rounds. We are just trying to get a sense of how bad can this algorithm perform in terms of regret, right? So we use the word regret. Let's get back to that expression. We use the word regret. Why did we call it regret? That's because if this difference is large, that means you're not doing something intelligent, right? We know that if you had a priori knowledge about all these distributions, you'll figure out the best arm, the k star which corresponds to nu star, and you use that k star, and so the expected cumulative regret is 0, right? 0. The expected version is 0, yeah, but this can be whatever. Expected cumulative reward is 0 if you use the k star corresponding to nu star, right? The arm corresponding to nu star. So it's called regret because it's talking about this difference. And if the cumulative regret is small, it's not growing linearly with the number of rounds. It means that you're doing something intelligent as the number of rounds are progressing. Okay. Or alternately, you can actually look at so if I divide by n, it's basically some constant times k times log n divided by n. This is what the two plots were trying to kind of show, in the sense that I was saying if I keep other things fixed, it grows linearly with the number of arms. So if an instance has 100 arms, then people have actually proved a upper bound for any instance which has 100 arms. They can tell you what the maximum expected regret can be for this algorithm. Okay. And similarly for this, in the sense they've shown that the expected regret is upper bounded by some constant times k times log n, where k is the number of arms and n is the number of rounds. Okay. So you can see that the average regret actually goes to 0 as n tends to infinity. So as you're interacting more and more, as you're pulling these arms or trying out actions, you're doing something intelligent, right? As let's say n is 10,000, you're not experiencing any regret on average. And when you're not experiencing regret, you've figured out you're pulling the right arm most of the times. That's why you're not experiencing regret.
Sorry.
Yeah.
If if you have the n in the denominator, any other kind of
n I just divided.
will always have, if n becomes infinity, it becomes 0.
No, if there is a n over in the numerator, then you will not. So the trick is to actually, I mean, so this is just a nice theoretical guarantee to have, that this algorithm, irrespective of whatever instance you give me, eventually will figure out, eventually will such that the instantaneous regret or whatever the average regret goes to 0. Or basically saying that the cumulative regret is upper bounded by some curve, which is like logarithmic with respect to the number of rounds. Okay. So let's look at one example, a synthetic example. So there are five Bernoulli arms here. 5 Bernoulli arms just means that the new 1 to new 5 are coin tosses, right? With biases, 4 of them have the same bias and one of them has 0.9 as bias. And this plot is showing as a function of time or number of rounds, what is the probability of selecting the best arm. Remember, this is a sorry. One second. Oh yeah. Yeah, this is the probability of selecting the best arm. So basically, it's epsilon. Okay. So there are 5 values of epsilon here. 0.5 corresponds to being. I mean, here they have just said it corresponds to an exploration type of strategy where mostly you're saying I'll flip a coin. If it's heads, then only I'm gonna pick the one, arm that I think is the best one. Or with tails, I'm gonna pick any arm at random, any of these 5 at random. Okay, so it just shows the probability of selecting the best arm converges to some number, basically, and they're trying to contrast between these two extremes, where if you're only planning to exploit, then you will figure out the best arm eventually, but it will take some time. And if you're planning to explore, you will figure out the best arm quickly. But since you're fixed on flipping the coin every time, even though you figured out the best arm, you're only flipping it with some probability, which is a little bit greater than 0.5 here, but that's what it means. Is this algorithm clear? By the way, this is the algorithm. That's it. This is a strategy which theoretically will do fine if you just think of in terms of expected regret, and in terms of empirically, how does it perform in this 5-arm case? How quickly will it figure out the best arm is just being captured in this experiment? Yeah.
Whether it is a businessman or a scientist, the expected value of the regret over a long period of time will always be the same for both.
No, this will have more regret, right? So scientists will have more regret because it's not selecting the best arm. It's only selecting the best arm very close to 0.5, right? So half of the time it's selecting suboptimal arms. So it's only collecting these rewards in terms of mean value. So about 0.4 times 0.4 probability, it's collecting rewards like this, and with 0.6 it's collecting 0.9, right?
The final regret equation is based on the board.
This is not final regret, right? Yeah, I mean, but regret. This is just an upper bound. This is not the. So this is just an upper bound. We are saying that this algorithm. Yeah. So in the sense, both of them will have instantaneous regret 0. That is given, but scientists will have more regret than businessmen. There will be a gap in those curves, is what I'm saying. That's all.
So over a longer period of time, scientists will perform lower than.
No. I mean, eventually both will figure out. So in fact, they figured out the best arm, right? If you only cared about figuring out the best arm, it's just that even after figuring out this scientist is using is trying out the suboptimal arms still because epsilon is fixed, so you still have to flip the coin, right? So both algorithms are supposed to have an upper bound regret which goes to 0, I mean the normalized regret goes to 0. So both settings will go to 0. It's just they will have different.
Both will have performed equally well.
Yeah, equally well in the constants hidden and so on. But yeah.
What exactly it means by the scientist strategy doesn't exploit at the end?
I mean, it has figured out. So, scientist strategy is all about it's close to 0.5, right? So it's flipping. Let's say in this case, I have 5 arms. Okay. Doesn't exploit at the end in the sense when you explore, you're getting information about all the arms, right? In this case, 5 arms, but you can say I got information about all the arms. But even if I know, so after some amount of time, if I try all the arms, I would of course know their mean values, right? If I had infinite time, I can flip the first arm 100,000 times, second arm 100,000 times, and get the exact mean value for all the arms, right? But even if I know that, because I fixed the epsilons in this particular algorithm, I will still try the other arms.
You always pick it up using 0.5 plus.
Yes. You can think of another variant where you are changing the epsilon to 0 after some amount of time, so that it doesn't, it starts exploiting after some time. You can do that. That's going to be a variant, but this is one warm-up algorithm. Okay. So now let's look at another algorithm in the stochastic setting. I'm calling it a stochastic setting because the arm rewards are random variables. Okay. So this is a slightly different algorithm. It's called the upper confidence bound algorithm, UCB. Okay. And its strategy is going to be as follows. At time t, it's going to pick that arm which maximizes this expression. Okay. So what do I mean by that? At every time t, at every little index t, I'm going to maintain a number for every arm. Okay. That's on my side, right? I can keep a number for every arm. That number is going to be b subscript this of k. Of k just says for the kth arm I'm going to keep a number. Subscript t represents I'm going to keep a number. It can change in the next round, right? And t subscript k t minus 1 just means how many number of times was this arm used in the was this particular arm pulled, or I use this arm up to time t, right? So okay, I deleted that table. Right? So this is n. This is the strategy. So maybe my strategy, I'm just saying I pull first arm and then second arm, then first arm and first arm in this instance. Okay. Then how many times did I pull the first arm when t index is, let's say, 5? Okay. Here I want to. So at the 5th index, I want to say, okay, let me look back up to t minus 1 and just ask how many times did I pull arm 1? 3 times. How many times did I pull arm 2? 2 times. So that's what's being captured in that expression t subscript k t minus 1. Okay. So for an arm, after the previous time instance, how many times did I pull? Okay. So is this clear? I just want to maintain one number for each arm. So in the 2 arm case, I'm going to maintain 2 numbers. The 5 arm case, I'm going to maintain 5 numbers. These numbers are indexed by both arm and the time, because I may change this vector of 2 numbers or 5 numbers at every round, right? And tk minus 1 is just saying, I don't have to explicitly keep that as an index, but I'm just saying that will be useful for my that will be useful for the computation of this number. Okay, so this index is actually redundant. Okay, so what is this number that I'm going to maintain? So this number is going to be is going to have 2 parts. Okay, first part is called new hash k, and the second part is just some constant. Okay, in the sense it doesn't depend on k. I mean the outcomes feedbacks of k. So what are these 2 numbers? Okay, let's tease it together one by one. Tease them out. So the first expression is the simple empirical average. Okay, so I tried arm 1 right? 3 times up to this point, I'll get 3 reward numbers, right? So I'll take the average of the 3 reward numbers. That's new hat for arm1. Subscript s. So I've just replaced this quantity by s here. So it just says, okay, I tried this arm 3 times. So 1 by 3 times xk1 plus xk2 plus xk3. That is the 3 times I tried this particular arm. What was the numbers that I got as a feedback signal? Okay. It's just an empirical mean of particular arm at it says at time s. Basically it just means that I tried that arm 3 times, so that's why I take a mean with 3 numbers. If I tried that arm only once, then I just take a mean with 1 number, which is just going to be that number, right? And this second term is a fixed function, right? It's just a function of t. It's just if I'm at index t round t, then I take the square root of 2 log t. The numerator is kind of obvious. It's just a function of the round number. The denominator is again fixed, not a fixed quantity, but it's a kind of just a count. Number of times I've pulled that arm, right? That's what it is. Tk t minus 1 is just the number of times I pulled that arm up till the last round. So that's this now, this quantity. Okay. So these are just numbers that are associated with each arm, and then in this round I'm gonna just pick the arm with the highest such number, and I'm gonna try that arm. Okay. And that's it. That's the algorithm. So this is a strategy. People call it. Strategy is based on the optimism in the face of uncertainty. All it just means is that it's the same issue as before, right? I don't know the mean. If I don't know the distributions of the arms, so that's why I don't know which arm is the best. And I'm trying to try out different arms, right? In the epsilon greedy, it was clear which arm I was trying. The arm with the highest empirical mean is what I was trying with 1 minus epsilon, and arbitrary arm with probability epsilon, right? Here also I'm facing uncertainty. I don't know which arm is the best one. That's the face of uncertainty. Optimism just means that I'm gonna add an additional term to the empirical means and then take the decision of which arm to pull. Okay, so I'm just somehow removing that coin flipping part in the epsilon greedy algorithm and bringing in an additional bonus to the empirical mean, and then just deciding which one is the arm with the highest bonus values and just play that arm. So there is so this is that algorithm, UCP algorithm. Yeah.
Can you think about more intuitively about the bonus? Because the bonus is being added to all arms.
Yes. Yeah.
Second thing is you're dividing it by s. That means you want to use the arm that has not been used so far. I mean, you want to go towards that.
Yeah. So basically, it's a similar incentivization to the previous thing, right? If the arm has not been tried much, this term is going to be high compared to some other arm which has been tried a lot, because for that the same numerator but the denominator is huge, right? So if this term is going to be high, maybe that combined effect is that the bonus is high so that you try that arm because it has not been tried much. So that's the intuition for this. So if it has been tried a lot, then this term is kind of downplaying that arm. Don't try it again. But then that arm may have a really high empirical reward. Then you may still keep trying it, right? It's somehow implicitly trading off exploration and exploitation. So just quickly trying to wrap this particular algorithm up. So this one also has performance bounds in terms of expected total regret, cumulative regret. It's again upper bounded. So being upper bounded is good. Being very tightly upper bounded is even better. Okay. So in fact these plots are the same as what we saw in the epsilon greedy. So but these are just upper bounds. So here is a different experiment. So here there are 10 actions and actually million interactions. First of all, this may not be realistic in a real setting, but let's say in a million interactions. Reward for each action or each arm is has a mean of 0.5 divided by k. Okay, the mean value is 0.5 divided by k. So you can see that the first arm has a mean reward of 0.1, and then the other arms, the other arms have lesser and lesser rewards. Okay, mean rewards, and you can see that the cumulative regret is something like this. The function of rounds, you can see that it tapers off. That's a good thing. If cumulative regret tapers off, you can see that if you divide by n, it's 0, right? Constant divided by t. In this case, actually, it's the upper bound is ck log n by n, so it's tending to 0 as n tends to infinity. But you can see that this also kind of plateaus, and that's a good thing in the sense that this kind of signifies learning. In the sense you have essentially figured out what arm to exploit after some number of rounds. Okay. So let's stop for a couple of minutes and then resume. Yes.
What is IT here?
Your choice. I mean, I need to decide a strategy, right? Which means, what do I do at time t?
Okay, so I is the strategy.
I is just the index of the arm that I pick at time t. It can be one of the k values. It can be IT can be 1, IT can be 2, IT can be k.
Okay, so it's the index, basically the K, right? One of the
One of
values
the k values.
Yeah. Okay. And what is BT then?
It's just one number that you associate with each arm. Okay. It's like a vector. If you have k arms, you have a k dimensional vector. And each scalar is computed in this way: empirical mean plus some bonus. Empirical means anyway we saw in the previous algorithm. Just instead of taking the max of the empirical means, which is what epsilon greedy was doing, you take the max of empirical means plus a term which involves how many times that arm was pulled in the past as well.
So how are we capturing that? How many times was it pulled?
You just keep track of how many times it is pulled.
Like there's no term here, like
S. So sorry, tk t minus 1 was S here. But S is the number of times the arm is pulled.
Isn't
TK
it
T minus
S is the time because it says at time S.
No, it's not time. So empirical. So forget about this. So if I had pulled the arm S times, then the empirical mean is 1 by S times numbers, right?
Yeah.
So S just represents the number of times that particular arm that was pulled.
And I.
So that is the same as tk t minus 1. I just said, like, in this example, tk. So let's pick k to be 1. Then t1 of 4, t minus 1. Let's say we are at small t5. So in this is t. T is going to find. So t k. T minus 1. So let's pick up. K is going to be just 1 here. So this is actually IT. So IT as in time index t is equal to 1. This is index, time index, right? This is capital T is a good number of boxes. This is 2. A strategy is a sequence of answers. One, at any given point of time, what is the arm that we take is like a component of that strategy. The strategy is like the sequence of things that we do.
So K is my answer, so that one.
Yes.
What combination means we are using?
Yeah. Which time what?
So I can have multiple arms and based on that I can have multiple arms.
Yeah, with 3 arms you can have hundreds of strategies. One strategy is like full arm, one always. This is time index. Every time you pull a lever, which lever you pull depends on the strategy. Every time you pull a lever. Defined by the strategy. This is IT. I sub T is what you call it.
Given time t, which is 1.
Yeah. Yeah.
And this is part of the strategy.
Yeah. Then I'm just saying that DK is 50, which is the same as I'm just saying for an arm, let's say our time is 5. Up to 4th round, how many times was that arm? So T1 of 4, that's 3 times you use it, which is the S. So mean is going to be, new height is going to be 1 by 3 times, whatever the 3 numbers are. Some 3 numbers I get. It's just saying, it's just counting the number of times the arm is pulled up previously. You want to take a decision now. How many times scale is pulled?
It's like there's so much notation you get confused. Like
Okay.
I and D and then we
Okay, so we'll resume. Okay, we'll resume. We'll look at another algorithm. Which is called the Thompson sampling algorithm. Okay, it's a Bayesian algorithm. So the previous two algorithms were somewhat like keeping track of statistics, right? The empirical means and maybe add some bonuses and so on. So now we have a Bayesian algorithm. Okay, it's quite old actually, from 100 years ago. Okay, so this strategy, I mean, so the old algorithm was proposed for Bernoulli distribution. So actually, each arm was associated with a Bernoulli random variable, right? Bernoulli reward. So the distribution was 0. Distribution had the support the new k that I was talking about, the new k. Right? Let's say there were 2 arms. Again, we want a new 2. These are just coin flips, right? It can only take 2 values, 0 or 1. Maybe this is the unbiased coin, so the PMF is 0.5 here, 0.5 here. Maybe this other coin is has 2 outcomes with maybe this is 0.7, 0.3 here. For the second, that's all I mean by each arm is being associated with the Bernoulli distribution. Okay. Now, in any Bayesian algorithm, you're going to start with priors. Okay. So you'll assume a uniform prior on the parameters. Okay. So what is the prior on the parameter? So what is the parameter here? Actually, the parameter is going to be, if it's a Bernoulli distribution, the parameter is going to be the bias, right? Or a single number, which is the bias of the coin flip, right? Instead of writing it as P, I think I've used nu1 and nu2, which, if you remember, the bias is also the mean of the Bernoulli distribution, right? So in this case, it's between 0, 1, and so there's going to be, we're going to maintain, so we have some priors on the parameters of interest. So at any round t, what we'll try to do is work with the posterior distributions. So what are posteriors? Posteriors are also distributions on the parameters given data. Remember Bayes rule? So whenever you have data and you have a prior distribution over something or parameters, then you probability of theta given data is going to be the posterior, right? It's going to be proportional to something which is going to be the likelihood times probability of theta, which is going to be the prior for any prior in the Bayesian version of things. So now I'm going to have posteriors, and this posterior is going to be function of time index, right? So that's being represented as pi I of t. So in time index t, I have a posterior distribution pi I for the parameter nu I, which is going to be the parameter of that Bernoulli. Okay. And what I'm going to do is I have these posterior distributions for each of my arm. So in this case, I have 2 arms, I have 2 posterior distributions. I'm going to just draw sample from these distributions, okay, from each of these distributions, right? So these are sampled independently, just means what it means. So this is just drawn from this distribution, and then my strategy is just going to be, I'm going to get one number per arm again, and my strategy is going to be just take the index of that arm. I mean play that arm whose realization is the highest. Okay. So very simple strategy. In the Bayesian point of view, we always maintain priors and posteriors, right? Once we get data or evidence, we kind of update our prior distribution over the parameters. In this case, Bernoulli distributions, there are only two parameters, one parameter per distribution. This is going to be the bias. We're going to update our posteriors of this bias given evidence, whatever we've seen till now, and that's being written as pi I subscript t at time index t. And I'm just going to draw a sample from that posterior distribution for every arm. So I'm going to get, let's say in this case, two numbers. I'm going to pick that arm to try in this round, whichever, that arm which corresponds to the highest number. In this 2 arm case, in 10 arms case, you're going to sort them and figure out the index of the highest number, and that's what you play. Okay, so that's Thompson sampling. Okay. We're not going to delve too much into this algorithm, except saying that it has the same expected cumulative regret upper bound, have same dependencies as the UCB algorithm. So logarithmic in the number of rounds and linear in the number of arms. Okay, these are nice guarantees to have, that we know that these algorithms eventually will learn for any instance, right? You can't. So these are statistical guarantees, similar to the computational guarantees that you see in algorithms course and so on, right? So just making the prior and the posterior part clear, at least we'll not go into too much of depth of this particular algorithm, but just a recap of some of this that you might have already seen. So if you pick an arm I subscript t, that's what we picked at round t, right? Then the Bernoulli random variable, let's call it y subscript t, okay, which has a mean of new subscript it, right? It is just something that we picked. It could be either 1 or either 2 in this case, in this example. So let's say it is 1 for simplicity. Then I pick the first arm. I will see a number which is going to be a realization from the Bernoulli distribution, which is going to be 0 or 1, right? According to the parameter of the first arm, which is going to be new 1, right? So that's what I'm just grounding what exactly is meant by drawing from that. What is meant by playing that arm it. You just get a realization from the distribution corresponding to the. You get a realization from the corresponding Bernoulli distribution. Now, what is this? What is interesting is that for a Bernoulli distribution, you can have a distribution on the parameter nu I to be a beta distribution. Okay, so previously I said just pick a prior. Okay, in fact I said a uniform prior. So beta 1, 1 is actually a uniform distribution. So anyway, what I'm saying is, if you pick a particular prior, in particular it's going to be the uniform distribution or a beta distribution, then what you'll see is that the posterior is also a beta distribution. So this property is called the conjugate prior property. So the beta distribution is called the conjugate prior to the Bernoulli distribution. Okay. I don't know how many of you are following this, but so we have this Bayes rule, right? I didn't write out the full Bayes rule, so let me write it out. So let's get rid of this material. So what is this? Probability of data so this is what Bayes rule was, right? Is So what is data? Let's say we just observed one thing. So our theta is going to be, parameter, right? So our theta is going to be nu1. So probability of nu1 given what we observed, y is equal to y. It's just going to be probability of y is equal to y given nu1 times the prior. That's probability of y. Right? This is base rule. And what I'm saying is, if you assume this to be the beta distribution, and we know that condition on nu1, my outcome is actually Bernoulli. So this was fixed. This is just from the distribution that I attached to the arm. So if this is beta, this is Bernoulli. This is also going to be beta. Okay, that's all is meant by conjugate prior. So beta is conjugate prior to the Bernoulli distribution, or in general the binomial distribution as well. But here it's Bernoulli. Okay. So what does conjugate prior help us in the sense? Remember, if you actually need to compute the posterior distribution, posterior over nu1 given data, you actually have to multiply these two out. Okay. This is actually so you have to actually compute this for every value of nu1, right? Nu1 is random variable, right? And you also need to do this, which is going to take it's basically a integration over the joint distribution, basically, right? So what I'm trying to say is that if these distributions are not conjugate, then you'll actually have to do a hefty integration, okay? Especially with the denominator. What you can see is that if this is beta distribution, this is also beta distribution, then you just have to update the parameters of the beta distribution. So beta distribution has a parameter, right? So I don't want to write the parameters, but there are two parameters for beta distribution. Okay, two scalar numbers. So if this is a prior, and let's say the outcome was 1 or 0, then the posterior is also beta distributed with parameters which are just modified. Okay, only the parameters are modified. You don't have to do actually an explicit integration or something like that. That's all. Okay, and beta distribution looks like this for different values of alpha and beta. Actually, for 1, 1, it's a uniform distribution. Okay. Okay, so that's so we have seen 3 algorithms. Okay, so now we're gonna look at a couple of one other algorithm. Okay, we're gonna look at one other algorithm where we don't make any assumptions on the arms, in the sense that if I take an action, I'm assuming Bernoulli distribution for Thompson sampling, some other bounded distributions for the UCB and epsilon greedy, right? So I'm not gonna make any assumptions about how the rewards are generated, right? And the motivation is that these rewards may be the output of a complex process. So think of the website example, right? So let's say the user clicked. You showed an ad. You had 5 ads to show. You showed one of the ads, and the user clicked on it, right? Why did the user click on it? It's not probabilistic, right? There may be a complex chain of reasoning for why the user clicked on that ad. So maybe probabilistic modeling is not the right way. And in fact, you can also kind of assume that the rewards are generated by an adversary who is not random, or it can also be somebody who's actually trying to game the system. Also, they may also click arbitrarily, right? So just a couple of reasons why assuming distributions may not be a good idea. And what we'll show is that we can in fact do this. So we can get rid of the assumption on the distributions over arms, distributions associated with each arm, and still get some interesting strategy. Still get some interesting algorithms. An algorithm, the UCB algorithm corresponds to a strategy. Thompson sampling corresponds to a strategy, which is the I subscript T, right? That's the how do you compute which arm to pick in each round. So we'll study again in 2 settings: full information and bandit information. So bandit information is what we have been looking at, and we'll make this point clear now. So again, the template is now the adversary selects a bunch of rewards. Okay, adversary as in somebody on the other side selects for a given round a bunch of numbers. Okay, these are the rewards. These are the feedbacks I'm gonna give beforehand. In the sense I choose these feedbacks that I'm gonna give. If the agent, or if I'm gonna select if the player is going to select one of the index, right? So I'm just saying that, okay, the adversary pre-computed what he wants to respond back, okay, for all the k arms, okay. These are not known to us, okay, at round t. I select an arm it, right, which is what I've been doing, and in the bandit information, the player only sees the reward for the arm that they picked, which is what we have been doing as well, except that these rewards are not drawn from distributions. This reward is just adversary pre-selected a vector, right? So I'm just going to take that entry from that vector, okay. Full information setting just means that the player sees the whole vector instead of just the index of the arm that they played. Okay. Yeah.
In the previous settings, when we talked about rewards, it was for the player. This time, what exactly is it about? Is it for the adversary or is it for the player?
No, the adversary selects rewards that he wants to give to the player. So there are two parts, right? So, player or we are always picking actions. The person picking the actions is the player, and somebody has to give me back some feedback signal. Previously, we were saying the feedback signal is generated from a distribution, so you can always model a user as a distribution. Say you're getting feedback. Now we're calling that other side an adversary, and that person has to give us a feedback signal somehow. So we are saying this is how they'll do it. They'll first generate a bunch of numbers and then just give us back the number which was indexed by I. There's a particular reason why we are doing this, because you can make a powerful adversary who will always give a feedback 0 for everything. Okay, if he sees what arm you're gonna pull, then I'll just give a 0 for that. Maybe some bad reward for that arm, so you'll think that that's a bad arm, right? So it's somehow kind of restricting the power of the adversary, but it doesn't matter. I mean, what I'm saying is this is the procedure by which we are going to assume things are going to flow. Okay, this is a weaker assumption than assuming distributions. Yeah.
I'm not clear. If
About?
the player is able to see xt1 to xt3,
No, if there is full information, then player will see this. No, later, right? Once he plays this, after that he'll.
after we play, we'll get to know what are all the rewards that are possible.
For the time index t. In the next round, the adversary will again generate a bunch of numbers.
Right.
Yeah.
So the previous thing, we'll know what are all the
Yeah.
possible rewards.
Yeah. That's just a full information case. I'm just throwing it out here because you will see a natural progression of the algorithm. We're going to devise an algorithm, and we'll see that it's just an extension of a simpler case. This is a simpler case where I'm getting more information per round. I'm not just getting information about the action that I tried. I'm also getting information about actions that I did not try. Right? If I had shown some other ad, maybe they would have clicked. That's what is being captured in the full information set. Okay. So again we have to define what is called regret. So regret again is going to be difference between what we do, right? The rewards that we get because of something that we do. At every time we are doing IT, which is our action. So based on our action, we're going to get a reward. So we are just summing that up, and we are saying, okay, what if you picked one particular action? Okay. What if you picked one particular action? Then you would only see it's like one index. I'm fixing the index. I'm just summing that up. Okay. That would be a regret with respect to a constant strategy. Okay. So if the constant strategy gets this much reward, I'm getting this much reward. I'm just calling the difference to be the regret with respect to the constant strategy. Okay. It can be positive, negative, or whatever. Now I'm just introducing randomness because in the sense of I'm saying I'm going to take an expectation because maybe I'm drawing IT. I mean I'm just choosing IT based on some. Maybe I'm maintaining a distribution over my actions and drawing the IT. So this expectation is just trying to say if there is some internal randomness that I'm going to introduce, then I'm going to take an expectation over that. Okay, that's because I introduced the randomness. Now the regret with respect to the best constant strategy is the max over this expectation. Okay, it's just getting rid of k. I can compute this for every k, right? Regret with respect to constant strategy 1, constant strategy 2, constant strategy 3, and I'm just saying what is the maximum regret across all these constant strategies, right? Now the interesting thing is I want to build an algorithm or a strategy which hopefully can minimize this. right? It's basically saying if there is an underlying, so if there was a true, picking the true one of the coordinates, one of the actions was the thing that you were supposed to do in every round. This one is just computing that quantity, because max over k is just affecting this term, right? The k index is only for this. What I'm comparing myself to, I'm just saying I want to compare myself to the one of the indexes which is the best, which is going to maximize my index, and I want to minimize this regret. It's just once you get rid of expectations, you have to define what is your comparison, right? So that's why I'm defining this as the expected regret compared to the best constant value. Sorry. Yeah. And if you want to be even more formal, you want to say I want to design an algorithm that is good for all reward sequences generated by the adversary. So adversary is going to generate in n rounds n such vectors, and my algorithm should be such that for any such n vectors, n such k vectors that I generate, I minimize Rn. So it's just trying to say what is the target that you want to reach. So because there is no probabilities, we are trying to like define targets in terms of constant strategies and best out of them and so on. But it's okay. So let's get to an example to ground it more clear, because the objective is still the same: maximize your expected reward. Right? It's just that the expectation is only about your internal randomness, because the adversary is just randomly is generating these non-random reward signals. Right? That's why that's the only variation here. And so let's look at the full information case. So let's say we are the player, and so we are deciding to show a weather widget on our app, on our site, and there are many options. So which one we should choose? Okay. So we have these k weather widgets. Okay. So I have k such guys. So maybe my action set is going to be one of these k guys, and I show one of these on my website or on my page, and the adversary kind of sees that this is what they want. Okay, they prefer this widget. Okay, if this was a widget, they would click. If not, they will not click. So once the adversary, but the adversary has to choose this before, without seeing what I chose. But once you see, once the adversary reveals what they actually want, from there I'm kind of comparing the mismatch between your widget and what the adversary wanted. So I'm just generating those reward signals now. Okay. Okay. Actually, here I'm calling the reward signals else, but that's fine. And I know that because I showed this and I adversary wanted that, I get some reward signal. Okay, I'm just calling that L subscript A, or in the previous notation it was X bracket IT. Okay, and but the interesting thing is the player also gets to see all the reward signals, right? In this full information case. So that's what full information means. So is this example clear? What does full information mean? I took an action, I'll get a reward signal because of that action, but I also get a reward signal for all the actions that I did not take. Okay. If I had displayed this widget and the adversary wanted that, then there's a mismatch, so I'll probably get a bad reward. I showed this, adversary wanted the same thing, maybe I got a good reward. That's the full information setting. Okay. In this setting, there's a very simple algorithm called the exponential weighted forecasting algorithm. Okay, and the algorithm is very simple. So just like epsilon greedy, it's very simple, which is as follows: you maintain a weight for each arm. Okay, a number for each arm, right? We have been maintaining numbers for each arms in the epsilon greedy, in the UCB, in Thomson we were maintaining posterior distributions, but here we are going to maintain a number, and at each time t, the player is going to select an arm, okay, from a distribution. So how are you going to generate this distribution? we're just going to generate a distribution by taking that number, dividing by all the other, all the numbers that I have for all the arms right now. If I have a number for each arm, I can convert those numbers, those k numbers, into a distribution, right? I can just take, for an arm, I can just take the current number divided by the total of all the numbers, sum of all the numbers. Let's say they are all positive, okay? So that's going to be a distribution. It's going to be a distribution over arms, okay? And I'm going to randomly pick an arm from the distribution, and that's it. Now what is that? So I pick an arm and I play that arm. I'll get feedback, right? The feedback, because it's a full information case, I'll get the feedback, which is going to be a k-dimensional vector, right? L1 to Lk or x1 to xk. Actually, again back to x. So if I get the feedback, I'm just going to add the feedback. So if I have shown this particular arm s times, then I'm going to if I'm shown this arm, we have seen so at round t, okay, we have, actually this is computing from the previous round. So at round t minus 1, I need to have weights, right? How did I define these weights? At the beginning I said the weights are all 1, right? But at round t, I need to have weights t minus 1, at subscript t minus 1. Or actually, at round t, I need to have these weights before so as to generate the arm, right? So pt is a function of wt, so I need to have these weights. These weights are going to be functions of whatever happened before. And in particular, the weight for the kth arm is just going to be the particular coordinate, the kth coordinate of all the reward vectors I've seen, all the feedback signal vectors that I've seen up to time t minus 1. Because I'm seeing the whole vector, I can just look up all the reward values that this particular kth arm would have gotten. I'm summing them up and I'm just rating it by an exponent. It's just a simple transformation, but to keep things positive. But otherwise, there's nothing else happening. It's just counting, adding up the rewards. Okay, that's it. That's the algorithm. So the strategy is to pick from a distribution over arms, and the distribution is defined by maintaining a bunch of numbers on each arm, and those numbers are, if you take the log, it's just a count. It's just a sum of all the rewards you've seen for that arm. Okay. And this algorithm is actually also called the multiplicative weights algorithm or the EXP algorithm, and this also has some nice properties in terms of the regret that we defined 2 slides ago. And so it's in fact, if you see, there is there is an additional log, additional square root and all that. So it's better than previous settings that we saw. Why is that? Because we are seeing full information. We are getting more information per round than the previous bandit setting, right? So that's why these upper bounds are better. So that's the multiplicative weights algorithm. Now let's come back to the bandit feedback. So I'm trying to the reason why I showed this algorithm, the EXP algorithm, was because the bandit algorithm is going to be very similar to that, which is as follows. So again, recapping what the bandit feedback was, we have k arms. I play a particular arm. So in this case, we pick an ad. Let's say ad for we picked an ad for a motorbike, but the adversary wanted let's say a bicycle. Then but in this setting, the adversary actually has the whole vector computed beforehand, but I get to only see the vector, the coordinate of the reward signal for the ad that I showed. Okay, this is the more realistic setting, right? This is the setting that we've been looking at from before. So the feedback is just the reward signal for the ad that we showed. Okay. So for this setting, the same algorithm that we saw before, maintaining numbers for each arm, is gonna again pretty much repeat, and it's called the EXP3 algorithm. Okay, the additional 3 is added over here. I guess because the 3 E's here. So what do you need to do at each time? So again, we start with a bunch of weights, right? And at each time, we select an arm again according to a distribution that we create over the arms, the k arms. So what is this distribution? This distribution is going to be, so remember, this was the same as before, whatever we were doing, right? This is just the numbers that we have divided by the total numbers. So that would have been a probability by itself over arms. But now we are adding a 1 minus gamma and a plus gamma by k, very reminiscent of epsilon greedy. But you can see that this actually, if you sum over k, this is also actually a distribution. Okay, you can see that, right? If you sum over k, the k goes away, and if you sum over k, this term is 1. So 1 minus gamma plus gamma, it's 1. So it's a distribution. Again, you will maintain the same thing. The weights for the k term is going to be, if you ignore the exponent change, and it's just a sum of all the rewards collected up to the previous round. But we have bandit feedback, right? So how do we get x of k in a round where we did not show that arm, or did not show that add? Okay. So the simple trick is we'll just set that x of x, we'll call it x tilde, and we'll just set it to 0. Because we didn't show a particular arm, so we don't know its reward. We'll just set it to 0. Okay. But that's not all. But the arm that we actually showed, we reward got. So the reward that we got was x of k. Okay. We're going to actually divide it by the probability of that arm, the probability that we use. So if I pick an arm I from this PMF, I can pick an arm I, and I also know the probability with which I picked it, right? Because this is a PMF, right? I just divide by the probability with which I picked the arm, and then do the summation for that arm. So for one arm, I'll not just take the feedback signal, but the feedback signal divided by the probability while adding up the reward signals. And for other arms, I'll just I'll keep 0 for that round where it was not used. Okay, so that's the minor variation, but this is the algorithm. And nice property about this is that even without the stochastic assumptions that we were making for UCB and epsilon greedy and so on, here also the regret is dying with a number of rounds, for example. So you can look at the average. So if you divide by n, you can see that it's 1 by root n, and that also goes to 0 as n tends to infinity, number of rounds tends to infinity, which means that you're actually learning. And also the dependence on the number of arms is also like this, but it's okay. If you look at a synthetic experiment, so you have 10 actions and about 1000 interactions, 1000 rounds. And again, I've chosen rewards. So in reality, I've chosen rewards for each action to be Bernoulli with mean 1 by k, where k is varying from 2 to 12. But we don't know that. Okay. Although the instance is stochastic, I'm assuming that I don't know anything about stochasticity. Okay. And I'm an algorithm, which is the EXP3 algorithm. I'm not assuming anything about the environment, and I can still try to minimize cumulative regret. In the sense, I'll play according to the strategy I just described in the previous slide. You will see that the cumulative regret is small. Okay, but you can see that it's still growing because this is a non-stochastic setting. There is no because the numbers can change from round to round. Okay, and if you see actually. This is just the weight over which arm was picked. You can see that one of the weights has almost gone to 1 and everybody else has gone to 0. Okay, so at every round you can kind of see what's the distribution from which you're picking the arm, and you can see that one of the arms is most preferred over the other arms. Okay, so that's it. So those are the algorithms for the multi-arm bandit setting. So what's the? Let's try to see what all we saw. So these algorithms are trying to explore to learn about the arms, the actions, or whatever choices that the agent wants to make. So we want to take actions, right? We want to change the ads, we want to change the content of our websites, we want to change drug to a better drug potentially if it performs better. Versus exploiting the knowledge. If you know that a particular ad sells well, then you want to show that ad maybe. So that's the trade-off that these algorithms are trying to capture. And we've seen these algorithms: epsilon greedy, UCB, Thompson sampling, and EXP3. I've just only told you the strategies, and the strategies are very simple. They get captured in like 3 lines, and so they're easy to also implement. And there are many others which can also take into account constraints and additional domain knowledge on the arms. So, but what are the issues with multi-armed bandit problem? So multi-armed bandit formulation, it assumes independence while claiming those guarantees. So I was showing that okay, the regret is cumulative regret is going to go down to 0 and stuff. So while claiming that, you want to use independence assumption, which may not be true, right? If I interact with the user in the next round, maybe there's a dependence in terms of the rewards, right? That's not captured here. Stochastic version assumes static distributions of rewards, in the sense users don't change. In the sense, if I show this ad today versus I show this ad 1 year later, it's going to have the same distribution of rewards, which may not be true. Okay. Say users can change behavior. So basically, think of it this way, right? 6 months down the lane, an ad for a sweater is not going to fare well, right? Because it's going to be summer, let's say. So that's exogenous. So something changed on the user side, and that's why you want to take actions which are dependent on the user profile, and that's why motivating the contextual bandit. So till now we saw that there was no context, and we were just picking one good action, and it need not be good at all in all scenarios, and that's the issue here. Also, there is no carryover effect from one interaction to the next. So if I interact with the user today versus tomorrow, maybe my ad kind of influenced the user to be more willing to buy a particular sporting good or a particular technology product tomorrow, right? That is not being captured, right? User can change behavior by seeing my recommendations or my ads or whatever, and this can be captured by reinforcement learning, which is going to be next couple of lectures. Okay. It's not used much in industry compared to A/B testing. I think primarily because this has worked really well. And it's quite simple. It's reminiscent of randomized control trials, so that's why you see a lot of companies doing that, and they also do multi-armed bandits, but to a lesser extent. Okay. And so let's look at the final thing, which is contextual bandits. Any questions before that? Yeah.
Why did we go from EXP to EXP3 when we are seeing that the upper bound is increasing?
No, EXP was for the full information case, right? When I know the full vector, I have the EXP algorithm. EXP3 is when I don't know the full vector. It's a regular bandit. It can be compared to UCB, epsilon greedy, and Thompson sampling, because I only get bandit feedback. So there's a difference between EXP and EXP3. EXP cannot be used for the multi-armed bandit problem. It was just a segue to say that if I had full information, I would maintain a distribution over the arms, so maintain the distribution over the arms and play according to that distribution.
So in EXP3 we don't have full information.
Yes, full information is a special case that we just digress, because EXP3 is just a enhancement of EXP when you don't have full information. Okay, so EXP is is a different algorithm compared to all the 4 algorithms that we saw: epsilon greedy, UCB, Thompson sampling, and EXP3. Those are the algorithms for bandit feedback setting, bandit reward signal setting. It is right. So let's say you make a prediction. So it's an online prediction problem. I make a prediction that this is a cat. The person says this is a dog. Then clearly you know, if I had shown the dog, I would be getting a reward of 1. If I showed the cat, it would be getting a reward of 0. If I showed an aeroplane, I would be getting a reward of 0. So you would know. It's just a question of what is the feedback signal. If the signal can be transformed into a full vector. If you predicted something as a cat and they come back and say it's not a cat, it's a dog, then you know the full vector. Because if you had predicted any other of the categories, you would have gotten as a 0 as a reward. If only had predicted dog, you would have gotten 1. So that would be the full vector. That way it's relevant.
Even in this setting it is, but generally in terms of rewards, you will not know what exactly the rewards are associated with.
Of other things. Yeah. That's what. In general, you won't know.
Can I add to that?
Yeah.
If you're doing an experiment like, so 3 people,
Yeah.
3 groups.
Yeah.
And we have 3 positive options. So we don't have 3. The question was, we will not get the rewards for all the 3 at the same time.
Yes.
So my question is, can we use reward from one group coming in for one setting, second group coming in for another picture, and third group?
That is what we are doing, right?
Okay.
Every interaction at every round T, I'm not specifying whom I'm interacting with.
Okay. So at a given time T, we can use the information from a different group for the whole picture.
We are using all the information up to time T, right? Those weights are capturing some information from all the rewards that we have gotten up to time T minus 1 actually, to take a decision today. They can be from interacting with group 1 or group 2 or group 3, it doesn't matter. Okay. So where did we go? Sorry. Contextual Bandit. So again, back to the website example, and we'll tie it back to the news recommendation example. So here, let's say in this case it's Yahoo. So user comes to Yahoo with a history, with the user profile. Yahoo chooses to present some information. Let's focus on just news stories because the other things may involve more things. And then the user reacts to the present information, clicks on some of the interesting news stories, and doesn't click on some of the user stories. So that's the feedback. So is the 3-step procedure that we talked at the beginning clear? This is a Yahoo page. You decide what to show, and they decide what to click, and that's the reward signal, right? And you want to interactively as in over rounds, choose the content and use the observed feedback to improve future content choices. Okay. But now your future content choices are going to depend on who was the user roughly, because we know a profile of the user. Okay. Similarly, in the clinical example, the patient comes with a doctor, but they will have this whole medical history and the symptoms and so on. The doctor chooses a particular action to take, in this case a treatment, and the patient responds to it by getting better or not. So there is a context based on which you want to take a action, and you'll get a feedback signal. You are the doctor, right? So the doctor wants a policy for choosing these targeted treatments for individual patients. So given this feature vector of symptoms or medical history, you want to just say which treatment to choose. This is reminiscent of these classification problems, right? Given a feature vector, I want to say, okay, take this treatment, right? It's reminiscent of that, but it's an online setting in a sense. I'll have an interaction, I'll get a feedback, I want to improve on the next interaction. Okay, so what's the setting? Every round we get a context. We want to find the best policy, in the sense, what do we do in that context, and we may not even see each context twice. Okay, and so it's different from map because there is no context in map setting, and we were trying to find single best action. So we were just trying to find one ad which would be the best, or one action that would be the best, right? Here it's context dependent of what you need to do, So let's now go through an example of what is meant by context. Okay, so let's say we still have ads. Okay, or you can think of these as news stories as well. Let's say you have 5 ads. Okay, these are the 5 ads, and say we have 4 policies. Okay, these are rules which will say if the user profile looks like this, prescribe this ad. If the user profile looks like this, prescribe this ad. I have 4 such rules. In the sense, not rules, these are recommendation policies. Okay, whatever be the user profile, I'll tell you which ad to show. Okay, so it's not just one rule which says if user profile then show this ad. It's like if user profile something, show this ad, but if user profile something else, show this other ad, and so on. There's a whole list which tells you precisely what to do for any user profile. Okay, so let's say there are 4 policies. Okay, these are basically these map context ads. In the sense, given a context, it will tell you what ad to show. Okay, now what we'll do is we'll not go into details of the policy, and let's see if we can actually do exp3. Okay, which we saw in the multi-armed binary setting. How will we do? How will we use exp3 algorithm here? One way to do that is to ignore this whole thing about ads and just think of my policies as arms, right? I am the agent. I have 4 policies. In one round, I'll say, okay, policy just say something. Do like let's say, doctor 1 prescribe the treatment, doctor 2 prescribe the treatment, doctor 3 prescribe the treatment in different rounds. So you're only making decisions at the level of policies. You're not making decisions at the level of what ad to show, because once you pick the policy will tell you what ad to show. Okay. So for exp3, it has 4 arms basically, right? So in round T, say the policies recommend the following. Okay, in round T, some context came, some patient came or some user came. They had some profile, and based on that, those 4 policies suggest 4 different. 4 ads. Okay, 2 of the policies showing one suggesting the same ad, but that's not relevant to you. You care about picking one of the policies, right? Say exp3 chooses arm E1. Okay, by sampling from the weights. You had those weights, you normalize the weights and you sample from that. And so E1 is ad choice. So E1's ad choice, A2 was clicked. In the sense, even was a policy that you chose. Even suggested show add 2 or item 2, and item 2 was shown and it was clicked. In the sense, you got a positive feedback. Okay. Now, and that's what I just rewrote it at the top. What does exp3 do? exp3 assigns reward this x tilde. This is going to be x divided by the probability with which I chose that policy. This rescaled number to be my reward signal, and just add it to my counts, the W weights that I was maintaining, right? And rest of the arms will get reward 0. This is what we had agreed on, what exp and exp3 do, right? So this is the exp3 algorithm. I just repeated it, but let's kind of remember what it is. So can we do better? And that's where the context is helpful, is that yes, we can do better, because E2 was another policy which is also recommending add or item new story 2, right? So we should better estimate the reward of policy 2 as well, right? Because previously we were setting the policies 2's reward to be 0, whereas now we want to set it to something different. So that's the use of context. Okay. Okay, so what is it formally? Just a repetition again. So for t is equal to 1 to capital T instead of small n, the world produces some context. So now I'm calling context as x because we have used x as feature vectors, right? At as the action, which we can choose from 1 to k, and world reacts with the reward rt, okay, which is going to be a function of the action that you choose. Just like before, so if you take some action, you get some reward, okay. And we are not going to make any stochastic assumption, okay. And the goal is to learn a good policy choosing actions, policy for choosing actions given context, okay. So what does learning mean? We want to efficiently compete with a class of all possible policies. What are policies? Policies are all functions from context to actions to take, right? Given any context, I want to suggest an action. So this capital X represents all contexts that are possible, all sorts of user profiles. For every user profile, I want to suggest which news item or which set of news items to show. That's going to be all policies, right? It's huge. So if this is the class of all policies, I'm going to define regret to be what did I do. So what did I do, which is what are the actions that I took, right? At every round t, I take some action, right? I get a reward signal. I just sum over all t rounds, so I get t reward signals. So that's this term. How does that compare with what's the best policy, what the rewards that the best policy could have gotten, right? So every round I get a context. The best policy, maybe the one which maximizes this, is going to pick a particular action to take, maybe an add or a news item, and you get a reward. You just sum over every round like that. Okay, that's the comparison with which I want to compare myself. I am taking actions 80 according to some strategy. Okay, I'm going to define a strategy now, but I'm going to compare myself to this. And the way to do it is this algorithm called exp4. Okay. There is an expansion for why there is exp4. There are probably 4 e terms in the explore, exploit, exponential weights with some another e there. But the algorithm is almost the same as exp3. So what is it? The algorithm is going to be, think of these policies as arms. Okay. So we're going to maintain a weight for every policy. Okay. So in that sense, it's an impractical algorithm if you have too many policies. Okay, if I could enumerate all the policies, I will maintain a weight for every policy. Okay, and I'm going to maintain a weight for every policy, and then for each round, okay, I am going to observe a context. So this was new. So before I was not seeing a context. So I'm going to observe a context, and again I'm going to compute a distribution over my actions. Okay, I'm not going to construct a distribution over policies. I'm going to construct a distribution over actions. That's different. because if it was EXP3, I would construct a distribution over policies. How would the distribution of actions look like? It's basically a sum. So let's look at the first term. It's basically the numerator is going to be the weight over each policy such that the policy suggests a particular action. So fix an action A. I want to collect all the policies which recommend this action, right? There's going to be a bunch of them. So that's just, we are saying for every policy, if that policy's recommendation for this context is going to be that action A, then I'm going to have a 1 there, otherwise 0, times the weight. It's just aggregating the weights of all policies which suggest the same action for this context, okay? And I'm just dividing by the weights of all policies, okay? This additional PMN is actually again reminiscent to the EXP3, so I will ignore that. So it's basically something to do with explore exploit, okay? So PMN is an exact expression, but we don't care about that. So what I'm saying is, this step we got a context and we are just creating a distribution over actions given weights over policies. That's the one step difference between EXP3 and EXP4. Okay, but once we construct this distribution over actions, we do the same. We draw an action from this distribution of actions and observe a reward, which is going to be the reward for that action. Right? We got a reward number similar. So this step is the same as what we were doing before. Now we update each. So we have to now update the weight over each policy. Right? We were maintaining weights for each policy. So now we got a reward number. We're going to update the weights of each policy. And how are we going to update that? It's written in a recursive form, but it's actually very similar to what we were doing in EXP3. If a particular policy, so let's fix a policy. If that policy was suggesting action A, then I'm going to do a division of the reward, the reward that I actually got, RTAT, divided by the probability with which I picked that action. Okay, that I'm going to just so here it's exponent. That's why there's a multiplication, but you can just think of it as W to the power. A summation is happening. It's just counting over all the previous rounds and just adding scale rewards or zeros whenever there is a this policy agrees with the action taken or doesn't agree with the action taken. Okay, this is just written in a recursive form. So this update rule is very similar to what we saw in EXP3. It's pretty much the same. Okay. Yeah, and you can see that EXP4 algorithm also has some nice theoretical upper bound guarantees, but it will also have, so in addition to dependence on the number of arms and the number of rounds, it will also depend on the number of policies in a logarithmic way, but it has dependence. But it's inefficient computationally because you're maintaining a weight over every policy. Okay, and that's gonna, if you have 100,000 policies, you have to maintain 100,000 weights potentially. Okay, that's why it's inefficient computationally. And so there are other more involved algorithms which pretty much do the same. Deal with context, deal with policies, and suggest actions. Okay, and we'll not go into them. So that's it. So that's EXP4. So let's now quickly wrap up. So what did we see? We saw Multiarmed Bandit, where we were taking actions, we were getting rewards, we were trying to figure out the best action, right? What changed in Contextual Bandit? What changed in Contextual Bandit is the notion of context. So, or I'm calling it state here. So depending on the state or depending on the context, we are taking an action and we're getting a reward. And the state also influences the reward, right? Because if the context influences the reward, if you saw the context influences the context. So both the action and the context will influence the reward. If for example I show an ad and I show an ad of sports and the person needs an ad of technology, then both will influence the reward to be low, right? That's all diagrammatically I'm mentioning. Okay, but this context can change exogenously in the sense tomorrow somebody else can have a profile. So I showed a particular ad, right? Today I showed an ad of, in this interaction I showed an ad of, I saw the context, it's below 30 years old IT professional, then I showed an ad of a tech product, okay? In the next interaction, there was somebody else who came in, right? Somebody else, maybe below 30 years old, but is a doctor. Okay, my action has nothing to do with that next interaction being with a doctor, right? My action has not changed and is not influencing the state, is what I mean. Is not influencing the next context, right? I show an ad today that has nothing to do with who's going to come tomorrow, with what context. There is no influence. Okay, that's what is assumed in contextual bandits. Okay, so the ads I show today have nothing to do with people who come tomorrow, but that's not true, right? The ads that you show today, maybe you kind of show only technology ads. Maybe tomorrow only technology people will come to your website, right? So that's the notion that your action, your ads that you show, is going to influence which user is going to, which context is going to come in next round, and again the ad that you show to that context is going to influence which context is going to come in the next round, and so on. In the sense, the change of the context is not exogenous. Your actions, your ads influence which context come tomorrow and day after, and that's the reinforcement learning problem. So those are the three problems. Any questions so far? So to summarize, we looked at A/B testing as a way to introduce enhancements in a business product, but that was simple. We had just two things that we wanted to compare. We needed potentially may need a lot of examples, and this is based on the idea of randomized control trials, and is dependent on the hypothesis testing literature. We also looked at two online machine learning problems, which are the Multiarmed Bandit problem and the Contextual Bandit problem, and this Contextual Bandit solution is the one which powers Microsoft's MSN.com website in terms of recommending news articles, right? And Contextual Bandits are special cases of reinforcement learning, which we'll study next time. So that's it. Thank you.